Thank you very much, Rachel, for the introduction. And thank you very much to everybody for coming along tonight and I guess devoting your Friday evening to physics. So the subject of tonight's lecture is, as Rachel said, is the first direct detection of gravitational waves. And this was sort of a inspiring and deeply fundamental discovery that was made in 2015, was announced in February of this year. So the plan of the talk in three parts. Firstly, I'll tell you what are gravitational waves. Then we'll look at how we detect them and what exactly it was we saw, or more correctly, what we heard during the first detection. And then why this is so important and why we say that this heralds the beginning of a new era in astronomy. So, let's start with part one. What are gravitational waves? Well, as many of the people in the audience may already know, these are ripples in the fabric, or sort of more precisely the curvature of space and time. But what do those words actually mean? So what I'm going to do is take the next 15 minutes to turn you all into experts in Einstein's theory of general relativity, full maths. I'm just kidding. And then we will be able to appreciate what these waves are, and then we can go on to talk about the first detection. So the story begins actually in the late 1900s. It was a few years before Europe sort of descended into the chaos of the First World War. This photograph was taken at the Solvay Physics Conference, which was held at the Hotel Metropole in Brussels in 1911. And there are some quite famous names and actually faces in this photograph. Max Planck, Count Louis de Broglie. So those two gentlemen were two of the inventors, basically, of quantum mechanics. Marie Curie, winner of not just one, but two Nobel Prizes in physics and chemistry. Ernest Rutherford, friendly Kiwi. So those last two were heavily involved in the first studies of radioactivity. And then, of course, Albert Einstein. I should say, by the way, that the other people in this picture are not exactly nobodies. You've got Sommerfeld and Lorentz and just Debye and everybody there, but I don't have time to talk about them, so we'll just stick to those five. So at the time that photograph was taken, physics was actually undergoing three simultaneous revolutions. The first was quantum mechanics, the idea that atoms and light simultaneously behave as waves and particles. And also the idea that atoms emit and absorb little packets of light, which we call quanta. Secondly, Einstein's special relativity, the idea that time and space are not absolute. If you're moving quickly, your clock is ticking slower. If something else is moving quickly past you, then its length gets foreshortened. And those two things together, for consistency, then imply an equivalence between the energy E and the mass m of the particle. So that's the famous E equals mc squared, the rest energy of a particle. And then the third one, radioactivity, which is a sort of combination of the first two, and it led to the transmutation of elements and what we now think of as nuclear physics. So, at that time, Einstein was struggling with how to incorporate acceleration and gravity into his theory of special relativity. As many of you will know, special relativity refers to observers that are moving with respect to one another at constant speed. But what about if there is acceleration? What about if there's gravity? So Einstein was struggling with this, and he did a lot of thought experiments to try and work through the consequences. And I'm going to go through one of them here, just a simple one, to give you a flavor really of how this works. So this thought experiment is very, very simple. We just take an atom and we drop it through a height h. That's it. The atom is this, this green circle with a white center, so highly realistic. So let's do that experiment. We've got our atom. At the top, it has an energy mc squared. We've just learnt that on the previous slide. The mass of the atom, let's call it ma, therefore that's the energy. At the bottom, the energy is still mac squared, the rest energy of the atom, plus the energy that it has picked up due to the drop. And if you remember your high school physics, if you don't, doesn't matter, but if you remember your high school physics, that's just the mass of the atom times the acceleration due to gravity, which we call g, times the height, h. Okay. All right, now on the right-hand side of this page, we look at exactly the same thing in a completely equivalent but totally different way. So again, we drop the atom. But now, as soon as we drop it, the atom emits a photon which goes off to the right of the page. So that photon is the red squiggly line. What is the energy? Well, there's an mc squared for the atom. But notice this is now mb, not ma, because the atom has changed. It's emitted a photon. It's no longer the same atom as it was before. Okay? Plus, there's the energy of the photon, and I'm just going to call it E top. Okay, now we drop everything. We drop the atom, we drop the photon, and we also drop this mirror on the right-hand side for reasons that will become obvious in a second. And so just before the atom gets to the bottom, the photon is traveling to the right, it hits the mirror, which is falling as well, bounces back, and right at just before it gets to the bottom, this photon is reabsorbed by the atom. Okay? What is the energy? Well, mc squared, again, plus the energy that we get from the drop, which is mgh, plus the energy of this photon at the bottom, which is called E bottom. Okay, now I've tortured you with the example for just a little bit because I want to make a very important point. Both the sides of this page are completely equivalent. So this equals that, this equals that. And if you pull out your pads and pencils and do some extremely simple algebra, you'll see that that is impossible unless E bottom is bigger than E top. You can check that for yourself at home, but just trust me. In other words, the light ray has more energy at the bottom of the fall than at the top, and that of course means that its color is bluer at the bottom than at the top. Okay. So if we actually do that algebra, it doesn't matter too much, but you find that the ratio of the energy of the photon at the bottom to the top is 1 plus gh over c squared. And by the way, if you put in numbers for that, like for the Earth, say h is 10 meters, you get a tiny correction. gh over c squared is like 10 to the minus 15, but it's not 0. Okay? So the point still remains, the light turns bluer as it falls, and for reasons which I won't go into here, that means that time is ticking slower, closer to the Earth. Okay? Now that's actually a revolutionary idea. As you remember, Newton, and for centuries after Newton, believed that time is absolute. It flows equably without reference to anything external. That's a very beautiful language, actually. Without regard to anything external. That's not what's happening here. Here, there is regard to the Earth. When you're closer to the Earth, the time is ticking slower than when you're far away. So that revolutionized our thinking of time. So Einstein was struggling with all of this. Okay, already we found something pretty weird. He did many other thought experiments which were even weirder, and he was struggling. And then in 1907, he had what he himself called the happiest thought of my life. And here is a little quote from his notebook. For an observer falling freely from the roof of a house, there exists in their immediate surroundings no gravitational field. And that observer is entitled to consider themselves as being at rest. Now, what does that mean? So let's do that thought experiment, and it is a thought experiment. Please do not do this at home. We throw ourselves off the roof and close our eyes. Okay, so what do we feel when we do that? If there's no wind rushing past, then all we feel is a sensation of weightlessness, and we have no way of knowing whether we're moving or not moving, falling or not falling. Right? Furthermore, if while we're falling, we throw a tennis ball away from us, if we then open our eyes and look at the tennis ball, we who are falling will see it going in a straight line, because everything is falling together. Right? You who see me falling and the tennis ball, everything is curved. But for me falling, it's all going in straight lines. Another equivalent way to think about this is pretend you're in a lift with no windows. And you have a sensation of weightlessness. That could mean that you're out in the middle of empty space somewhere, far from the Earth, far from the sun, whatever. There's no gravity. But it could also mean that you're on the Earth, in the Empire State Building, and some nefarious person has chopped the cord in the lift and you're just dropping down. Without any windows, you have no way of distinguishing between those two scenarios. That's what is called the principle of equivalence. It's the principle which underlies general relativity. Yet another way to think about it, say you're in that lift with no windows again, and this time you're not weightless. You take an apple, you drop it, and it falls. Okay? Well, that could mean that you're on the surface of the Earth, and there's the pull of gravity. Or it could mean that you're in empty space, far from any gravity. But that nefarious person is pulling on the cord of the lift with exactly the right acceleration so that the apple falls. Again, you won't be able to distinguish those two scenarios. Okay, now, though that principle of equivalence has deep consequences for the curvature of space and time. And to understand that, we can look at this thought experiment. So here we've got the Earth, and we're going to take two tennis balls. We're astronauts. We take two tennis balls and we throw them past the Earth, or towards the Earth. Now, as soon as we let them go, they are falling freely, right? So, by the principle of equivalence, as I said before, they must just be moving in straight lines in their vicinity. And furthermore, the coordinate grid in their vicinity, which is like the lines on a map, right? That coordinate grid is also going to be completely straight and flat. Okay? So that explains that picture there and that picture there. They're moving parallel. Now we go on a bit. Well, the tennis ball, of course, is being dragged towards the Earth by gravity. So its path will have deflected somewhat. But again, in its vicinity, it's falling freely. So in its vicinity, it's going in a straight line. And again, the coordinate grid in its vicinity is straight. Okay? And so on and so forth. That's true everywhere here. So what we are finding here is that locally, these coordinate grids, which are just another way of saying space and time, if you think about a map, the coordinate is just, the grid is just a way of telling you where you are. Right? The space and time in the vicinity of this ball is always flat. But globally, when you join the dots, join these grids together, they are curved. So gravity is curving space and time. Okay? So just to summarize that, very important point, freely falling bodies move in a straight line locally, but their paths converge globally. And so the coordinate grid, which as I said is just another way of saying space and time, is flat locally and curved globally. Now we need to talk about this for gravitational waves, because gravitational waves, basically we will try to look for these curvatures in the space-time. That's the whole point of the detection. Okay, now before we get to gravitational waves, this curved space has three important corollaries. The first is that what Newton, and in fact most of us, think of as gravity, as a force, Einstein says no, it's not a force. It's just the shortest, most natural path that a body follows in curved space. So I have a picture here to illustrate that. Here is the Earth, and this mesh kind of depicts the curvature of space around the Earth. So think of this, imagine you've got a giant trampoline, and you put the Earth on the trampoline. It's going to make a dip. Okay? And I've got a satellite there just for fun. It plays no further role in the discussion. Okay, so we take an apple, and we throw this apple past the Earth. What will happen? Well, imagine if this was the trampoline, right? We know the apple will roll along the trampoline, go into the dip, and then shoot out the other side. And in the process, its path will deflect. Normally, we would think of that as deflection due to the gravitational force. But what Einstein says is no, that is just the natural shortest path that this apple takes within the curved space. The second corollary is that it isn't just the paths of apples that are bent by gravity, also light. This idea is called gravitational lensing. And in fact, if the gravity is too strong, the light is bent so much that it can't escape. So if we return to our picture, here's the Earth. By the way, if the light can't escape, you get a black hole. That's what a black hole is. So suppose that we replace this Earth now with a black hole, much denser, and therefore the dip in the rubber sheet is much, much deeper. Okay. Now we take a torch and we shine it up out of the dip. Well, the ray of light comes out following the natural shortest path, and that natural shortest path is curved, and if the dip is too deep, it'll just curve around back on itself and fall back in. Okay? If it isn't too deep, then it will get out, but it will still have bent. This idea of gravitational lensing was actually very important as one of the first tests of Einstein's theory of general relativity. So in 1919, the astronomer Arthur Eddington sailed down to the southern hemisphere to look at an eclipse. And an eclipse is great because during a solar eclipse, the sky is black, and you can see the stars behind the sun, which you can't normally do. And what he saw was that the apparent position of the stars behind the sun had shifted relative to where they should have been. And that is because the gravitational field of the curvature of space-time around the sun bends the path of the starlight in the way that's shown here. Okay? So that was a direct test of Einstein's predictions. And we've seen this gravitational lensing now in many different places. On the bottom here we have a beautiful picture from the Hubble Space Telescope. And what you see is a cluster of galaxies. This is a huge group of galaxies many, many light years away in the distant universe. And these arcs are the result of this gravitational lensing. And in fact, Rachel is one of the world's experts in modelling gravitational lensing from these sorts of situations. On the right-hand side, we have a clip from the New York Times of 1919, a slightly sensational report of the discovery by Eddington that Einstein was right. I especially like this: men of science more or less agog over results of the eclipse. Anyway, okay. Now we need one more thing before we talk about gravitational waves. This is the last thing. When we try to measure gravitational waves, we will be trying to measure the ripples in space-time, the curvature of space-time. Now, if you want to measure the curvature of a balloon, it's easy. You're looking at it from the outside. You can see it's curved. No question. It's embedded in a space, and you look at it, it's curved. But you can't do that for the universe. There is nothing outside the universe. You're in it. So how can you possibly measure the curvature of the universe when you cannot get outside it? Well, to do it, you use the same trick as an ant, a clever ant, would use on the surface of the Earth. So suppose we have a smart ant. They can't look up or down. The only thing they can see is the surface of the Earth. But they want to measure the curvature of the Earth. How do they do it? Well, they take an arrow, as shown here, let's say like the yellow arrow, and they walk, or crawl, whatever. They walk with it, always keeping the arrow parallel. Then they turn the corner. I can't do that here. I'll turn this way. And keep doing the same thing, keeping the arrow parallel. Then they turn the corner again, keep doing the same thing, until they get back to where they started. Now, if you perform that procedure in a flat space, like a sheet of paper, common sense says that the arrow will preserve its orientation. It'll just go back to where it was at the beginning. But if you do it on the sphere, like the Earth, you can see here what happens. The arrow rotates by 90 degrees when you return to the beginning. And that's a completely local measurement inside the sphere. So the ant can work out that it's on a curved surface, even though it can't look outside the surface and is confined to living upon it. Okay? And that's very important for us. We want to measure gravitational waves. We're in the universe. We can't get outside. This procedure is called parallel transport. Okay, just for fun, the artist Escher is really fond of thinking about curved spaces. So in this circle limit 1 piece, he's actually looking at what's called a hyperbolic space, hyperbolic geometry. And for those who care about these things, the arcs that you see here in these lines are the geodesics of that space. Also, just for fun, here are 2 pages from Einstein's notebook when he was devising GR. So on the left-hand side, I'm not expecting you to follow every line here. On the left-hand side, this boxed thing is the mathematical object that we use to talk about curvature in the theory. We call it the Riemann tensor. He called it the Grossman tensor after his friend Marcel Grossman, who taught him all of this mathematics. On the right-hand side, we have this mathematical object, which is basically the thing that he uses to write down his field equations, as they're called. Today, we would call it something like the Ricci tensor. He called it the gravitation tensor. I'm not saying this because I think you should absorb it. I'm just showing you they're very beautiful notebooks, basically. And Einstein was not above a bit of doodling. So on the inside cover of the notebook, look at what he's doing. He's playing around with the famous 64 equals 65 trick that you might have come across in sort of toy books. Okay, so that's it. We're now experts in general relativity. The next step is to say what are gravitational waves. Okay, so I go back to here. Pretend we've got the Earth on the huge rubber trampoline. A giant hand comes in, grabs the Earth, and bounces it up and down. What happens? Well, we know, common sense, there will be a ripple going out on the trampoline. That ripple is a gravitational wave. We don't have a trampoline, but it's a ripple in the curvature of space and time. So, any accelerated, lopsided mass will make gravitational waves, and the ripples propagate through space-time at the speed of light in Einstein's theory of general relativity. Now, there are other very respectable theories of gravity where this is not true. The speed is a bit different to the speed of light. And one of the big goals of gravitational wave science is to do ever more precise experiments to attempt to test this prediction. As I said, anything massive can create gravitational waves if it's moving. So this couple dancing the tango, they are making gravitational waves. When I wave my hand like this, I'm making gravitational waves. They are extremely weak, and we could never detect them. But, well, not never, but certainly not now. But gravitational waves are being produced. More practically, actually I'm not sure if practical is the right word there, but more practically, if you have 2 black holes orbiting each other, then that will produce gravitational waves. We'll talk about that in a second. Cosmic explosions like this supernova, this is the Crab supernova in about 1,000 years ago, make gravitational waves, and also the Big Bang made gravitational waves, we think, and I'll talk about that in just a sec. Okay, so that's the end of part 1. Now, part 2, the first detection, direct detection. how do you detect these gravitational waves? Well, we've just heard they're ripples in space and time. So maybe naively you'd think it's like having a cork on the ocean. If I have a mass there, an apple, whatever it is, gravitational wave comes past, the gravity is changing, the apple moves, and I can detect them. But think about what I said about the principle of equivalence. If I'm sitting on that apple and I close my eyes, right, I'm just falling freely, I don't know whether there's any gravity. And I don't know whether there are any gravitational waves. Just looking at one apple can't do the trick. You have to have two corks or apples bobbing on the ocean, and then you measure the distance between them very accurately, and that will give you a gravitational wave detection. The strength of the gravitational wave is quantified by this thing we call h, the wave strain, and that's defined very easily. It's just the change in separation of the quarks divided by their separation. But the thing is, this number is usually tiny. Like the best we could hope for from black holes and everything else in actual practice is like 10 to the minus 22, which is a tiny number. To give you an idea, if we take a separation of 4 kilometers, and you'll see why I've chosen 4 kilometers in just a second, then the change in separation is 1,000th of the size of a proton, subatomic particle. So that is the most precise and challenging length measurement that humanity has ever attempted and now succeeded. Okay, so how do you do this? Well, you ask the US Congress for $500 million and you build two of these. And this is the Laser Interferometer Gravitational-Wave Observatory, known as LIGO. And this one is in Hanford in Washington State in the US, and there's a twin in Livingston in Louisiana, in the bayous, in the swamps. So what you are seeing here is a giant Michelson interferometer. For those who don't know what that is, I'll explain in a sec. We have vacuum arms, 4 kilometers long, which is why I chose 4 kilometers before. Inside these arms, high-power lasers, which measure the length of the arm to sort of phenomenal accuracy. At the ends of the arms, there are beautiful mirrors that have been made out of like perfect gemstone, like a perfect silicon crystal, for example, and which are suspended very delicately to protect them from the environment. So as a gravitational wave passes through, the mirrors move like this, and the lasers measure the distance and make a detection, measure the changing distance and make a detection. There are others in the world. So apart from the two in the US, there's one in Pisa, very appropriate, called Virgo. Another one in Germany, which is smaller. There's one called Kagra in Japan, which is actually underground, very close to the Tokyo metro. So that's quite a vibration-full environment, but still, it works. It's being built and is working very well so far. And then we have our own little baby in Gingin near Perth. This one is too small. It's only 80 meters. It's too small to actually detect anything. But it's an excellent test bed for technology development for the other detectors. And Australians have made actually big contributions to LIGO through Gingin and through work at ANU and Monash and other places. Okay, now here again we have the interferometer. Don't worry about the diagram, it's not too important. Here are the lasers, there are the mirrors. What I want to focus on is, oh, and by the way, 10 milliseconds for light to go from one. So when a gravitational wave hits the Hanford detector, it'll arrive at Livingston 10 milliseconds later. What I really want to concentrate on is the picture at the top right. So this shows you the noise in the detectors, the two of them. On the vertical axis, we have that quantity h I mentioned before, the change in separation divided by the separation. Actually, it's not exactly h. It's something very closely related to it, but I don't want to get caught up in those details. On the horizontal axis, we have the frequency in hertz, and you can see it's sort of hundreds of hertz. So that's in the range of human hearing. And there are three main noise sources in this thing. Now, by the way, the numbers are tiny, so this instrument has hardly no noise in it at all. But unfortunately, the signal is tiny as well, so we really need to understand this noise extremely well. At the high end, the noise is called shot noise from the lasers. So the lasers are actually made up of billions of photons, and those photons are hitting the mirrors like rain falling on a tin roof. And so it causes the mirror to rattle a little bit. Okay? But we are worried about little bits, unfortunately, in this experiment. On the left-hand side, we have seismic noise. So LIGO can sense the waves breaking on the beach hundreds of kilometers away. It can sense shifting of soil, when wind blows through the trees, it causes the roots to disturb the soil. LIGO senses all of that. And that's sort of over here. And then these spikes are called violin modes, and they are actually the violin modes for the suspensions of the mirrors, which are amazing suspensions, but still they do have some vibrations. And I have a picture of a suspension here just to show you. So there it is. It's a magnificent piece of engineering. Here is the perfect mirror. By the way, CSIRO has made these mirrors. CSIRO are the best mirror makers in the world. Okay, and of course this is to protect the mirrors from the environment. So that's the machine. Now we come to the 14th of September, 2015, just after breakfast, universal time. The machine saw the following thing. Now, there is both picture and sound, and I want you to listen carefully. So firstly, I'm going to describe what we're seeing, and then I'll play the movie. We've got frequency on the vertical axis, time on the horizontal axis. Time runs for about a second. Frequency is in the range of human hearing. Remember, 256 hertz is middle C. And what you will see is sort of a blotch of colour that goes up and to the right across both of these panels. The top panel is for the Hanford detector, the bottom panel for Livingston. Okay? And we will also hear the sound. Now, we're going to hear the sound several times repeated. It only happened once in reality, but several times repeated. We'll play it first at natural pitch, and if you have good ears, which I don't, you will hear the tone. But then we'll play it again at an elevated pitch, artificially elevated, so you can hear it more clearly. And then we'll go back to natural pitch and repeat it. Okay? So let me see how this works. I always shudder a bit when you try to play a movie in PowerPoint, but let's hope. People hear that? Hands up who could hear the whoop in the first, well, actually first hands up who could hear it in the elevated pitch. Okay, most people. Hands up, could anybody hear it in the natural pitch? Just a couple of people with good ears. Okay, so what did LIGO hear? Well, it heard a chirp, the rising tone, lasting for about 1/5 of a second. The chirp goes from about 35 hertz, which is a pedal C note on the piano, to about 150 hertz, which is the D note below middle C, roughly speaking. And this chirp comes from the merger of two black holes 1.4 billion years ago in a galaxy 1.4 billion light years away. So that little sound has propagated across the universe for basically 1/10 of the universe's life. 1.2 billion years ago, I believe there were no dinosaurs on Earth, not serious ones anyway. Might have been some little things, but nothing impressive. And of course the universe was somewhat younger as well. Now, from the sound, from the tone, we can infer that the two black holes are 29 and 36 solar masses. And from the end bit of the sound, called the ring down, I'll talk about it later, we can show that the final black hole, when the two merge, it has a mass of 62 solar masses. Now, the alert listener is saying, well, 29 plus 36 is 65, not 62. But 3 solar masses worth of mass has been converted into gravitational wave energy. And that's a huge amount. So for these 0.2 seconds, this event was brighter than all the other stars in the galaxy, and in fact in many galaxies. And by the way, just to emphasize, these two black holes which merged, it was 1.4 billion light years away. It's not in our Milky Way. It's in a distant galaxy in the early universe. This is a famous picture from the Hubble Space Telescope, the Hubble Deep Field, and what you are seeing here is photos of some of the most distant galaxies that we know. Okay, now here I'm going to play you another movie. This one doesn't have sound. This is a simulation of two black holes merging. The color scale gives you an indication of the curvature of space-time around the black holes. And what you'll see is that the black holes are doing an orbit. As the orbit progresses, this red line moves across. So this is at the bottom is an indication of the signal that we were hearing before, the tone that we were hearing before. So let me just, I hope this plays. Yep, there we go. So there are the two black holes. They're orbiting each other. As they orbit each other, they emit gravitational waves. So they're losing energy. And because they lose energy, the orbit shrinks. And so we'll see after a little while that the orbit has spiraled in and shrunk, just like there. And then the black holes are getting closer and closer and closer. Now they merge. And then there's this ring down stage where they kind of settle down to one black hole. And you would have seen there's a ripple coming out. And that ripple is the last piece of the gravitational wave signal. Okay? So what LIGO saw was basically the last few orbits and then this ring down, this last piece. And just for fun, here we see, that was gravitational waves. Now we're going to look at the same thing in visible light. This is not realistic, it's not to scale, it's really just for fun. Here we have two black holes, and they're just superimposed on a star field. And pretend that we can look at this through a telescope, which we can't because they're too small. But I play the movie, and what you'll see is the black holes are orbiting each other, and soon they will merge. And the stars behind them are being sort of churned because their ray paths, the paths of the starlight, are deflected by the gravity of the black holes. It's not that the stars are moving in truth. Their apparent position is changing. And there is the ring down and that final ripple that we got used to with the ring down. Okay, now, obviously this is the first detection, so LIGO wanted to make sure that they got it right. And they did multiple validation tests, which I'm not going to trouble you with now. But I will just say two things to give you an idea of how you can be sure that this is real. And the first thing is you can estimate at the rate at which the machine generates false alarms. The machine is constantly making false alarms, which are not real black holes. They're just chirps that come out of the noise in the machine purely by chance. Now, of course, common sense tells us that the there'll be many weak false alarms, and then occasionally, by luck, there will be a strong false alarm. So you can calculate that. And this graph, you don't need to worry about the details, but this graph shows you how many false alarms you expect as a function of the strength of the false alarm here. And you can see that by the time you get to a strength of 20, you expect no false alarms. And yet, the actual detection was at a strength of 20. So it is extremely unlikely that that is a false alarm, almost certainly real. The second thing that LIGO does, among many things, is what are called blind hardware injections. This is a kind of brilliant idea. So there is a little coterie within LIGO, a little team, whose job it is to, in secret, vibrate the mirrors mechanically in exactly the same way that you would expect for a black hole, for a merger. Okay? And they do it like once every few months, and they don't tell anybody when they did it, and they don't tell anybody how they did it. So then, let's say you've got a detection, like the first detection. You analyze the data, you argue about it, it goes on and on. You write the scientific paper, you revise all of this. Then you present the results at a giant LIGO conference. And once everything is presented, the director opens up an envelope and checks the secret list of blind injections. Yes. Yes. So interesting to think about why that is done, right? The idea obviously is to protect against two sort of countervailing psychological tendencies. One would be that detecting gravitational waves is very difficult, so even if you find something, surely it's not real, throw it in the bin. That would be one extreme. The other extreme would be gravitational waves are so exciting. Everything we see must be a real gravitational wave. And so this method kind of strikes very effectively, actually, a balance between those two tendencies. Okay, now what do we learn from each event? Well, from the basic tone, the basic chirp, you learn the masses of the initial black holes. From the signal strength and the theory of relativity, you get the distance. If you are lucky enough to hear modulations in the chirp, then you can infer, if you're lucky, the spins of the black holes initially, parallel to the orbital plane. You can also infer the perpendicular piece, but that's much harder, so I'm not going to talk about it. And you can compare how those measured spins compare with the maximum spin that Einstein's theory predicts for black holes. And then finally, from the ring down, after the merger, you can infer the mass and the spin of the final black hole. And it turns out the final black hole is always spinning a lot because you start with something with an orbit which is big, and that angular momentum gets transferred into something very small at the end. Okay, now, luckily, spinning black holes do actually make a very different tone to non-spinning black holes. So I'm going to play 3 of these here, and listen carefully. The first one, there's 2 black holes not spinning. So that's just like the first detection, okay, pretty much. Actually, no, that's not strictly true, but it's close to it. Now these are 2 black holes which are spinning. Listen carefully. Could everybody hear the difference? There's sort of a woo, woo, woo going on there. And for those who care, that's because the spins precess. And then here's a final one where this is just for fun, a little thing like a planet, say, is orbiting a spinning black hole. Again, I could do this forever, but I won't. Again, with that one, if you're interested to think like it starts off going like a motorbike and then it sounds a bit like the others. That's because to begin with, the orbit is quite elliptical. But as time goes by and the gravitational waves come out, the orbit becomes circular, and then it starts to sound like the others. That's roughly, I'm simplifying, but that's roughly what's happening. Okay, now, it turns out we were very lucky because on Boxing Day 2015, before breakfast this time, universal time, there was a second event. And I'm going to now play again for you one of those movies with the blotch moving across the screen and you can hear the rising tone. But what I'm going to do is, so there will be again the 2 detectors and everything else, but we will hear it 4 times. Firstly, we will hear the Boxing Day vent at natural pitch. Then we will hear the Boxing Day vent at an elevated pitch so that we can actually hear it. Then for comparison, the first detection at natural pitch and the first detection at elevated pitch. So again, listen and see if you can tell the difference. So it's Boxing Day natural. First detection. Okay. Okay, so what does the Boxing Day event represent? Well, again, it's a black hole merger, it turns out. And purely by luck, actually, again, about 1.4 billion years ago. But the difference is that the black holes are smaller, 14 and 8 solar masses. So the signal lasts longer, you can see more orbits, and that allows you to reconstruct the signal actually quite accurately. And this led to a very important discovery. LIGO found that the initial spin of one of the two black holes is more than 20% of its maximum possible value. That is a very cool result, and it's a very surprising result. Not entirely unexpected, but quite unexpected. And it raises kind of interesting issues about how these black holes are born. Are they born in star clusters? Are they sitting on their own somewhere? Do they accrete gas from a stellar companion? There's many possibilities. So this is a very interesting result, and we're all kind of really looking forward very keenly to the next observing run to learn much more. And the next observing run should be starting in a few months. Okay, so end of part 2, and now I come to the last part of the talk, a new scientific era. Up to today, astronomy has always been done with light. Now, light could mean radio waves, it could mean X-rays, it could mean gamma rays, it could mean visible light, which we can see, infrared, but always electromagnetic radiation, always light. There are actually at least two counterexamples to that can anybody think of a counterexample? Neutrinos, yes, so cosmic rays, neutrinos, other kinds of subatomic particles, which are not electric. Yep, completely agree. Dark matter we have never detected, but when we do, that will definitely be one, but so far not. The other example I can think of is you send astronauts to the moon and they actually pick up rocks. So it's still sort of electromagnetic, but not really. But anyway, bottom line, light. Light is what we use. And of course, light has been an incredible servant. What we've learned has been amazing. And here I just for fun have some photographs from the Hubble Space Telescope. So here is a photo of, anybody recognize? Mars. So you can see the carbon dioxide polar caps. This is a picture, I almost feel like turning off the lights. I won't, because that may do something bad. Here is a picture of a supergiant star, much bigger than the sun, which is kind of furiously putting out light and heat and shedding mass, which makes those beautiful shapes. I think it's called Monoceros. It's a picture of the Helix Nebula, which is, again, mass being shed by this time a dying star, a white dwarf at the end of its life. The beautiful Orion Nebula, which is the cradle, the birth cradle of stars. Those pillars are full of cold molecular gas, and those little red dots inside the pillars, here and here, are baby stars that are just starting to get warmed up. A galaxy other than our own, outside our own. I'm not sure which one it is. Rachel will know. It might be M31. And then the picture we saw before, the Hubble Deep Field, the most distant galaxies in the universe. All of this is with light. Now, gravitational waves have a huge advantage over light. I mean, they're hard to detect, that's the disadvantage. But the advantage is that they are neither scattered nor absorbed. That's why they're hard to detect, right? But that means that when you do detect them, you are seeing them kind of unadulterated directly from the center of the source. So it allows you to probe extreme physics in extreme environments which cannot be and will probably never be replicated on Earth. You know, the insides of black holes, the insides of neutron stars. So what can you do with this tool? Well, there's many things. The first thing is you can look for these black hole mergers that we've already heard. And by the way, that also includes neutron star mergers. So for those who don't know, neutron stars are dead stars. They're the result of a supernova explosion. They're basically as massive as the sun, but they're only as big as Melbourne. So they're very dense. And what we always say is if you go to the surface, which is highly not recommended, and pick up a teaspoon of neutron star material, then that teaspoon would weigh 1 billion tons. So you can get mergers of these neutron stars in the same way as the black holes, we believe. We haven't seen one yet, but we expect. And then with this sort of probe, you can do experiments on Einstein's gravity, very precise experiments, in what is called the strong field regime. Einstein's theory of relativity, which we learnt about in the first part of the talk, has been tested a lot in the weak field, on Earth, near the sun, all of this sort of thing. And it has passed every test with flying colours, no problem. But we have never tested it in this is the first time with these mergers that we're testing it in the strong field regime, like right near the surface of a black hole. It's very important to check theories across the full range of their potential validity, not just in one place. We've learnt that lesson hundreds of times in the past. And interestingly, if your space-time is not what we expect, like if it isn't a black hole, if there's something exotic like a wormhole or whatever, then this rubber sheet, if you think of a trampoline shaped in this way, and you bounce it, it will ring very differently to the space-times that we saw before, right? And so you can infer the shape of the space-time, the curvature, from the tone of the gravitational waves. In principle, this is not going to happen tomorrow, but it can be done in principle. And indeed, if there are extra dimensions in the world, you might be able to do the same thing. The second kind of astronomy you can do is to look at what's called the stochastic background. These are the gravitational waves produced by the Big Bang. So, to understand this, theory predicts that the Big Bang, immediately after the Big Bang, there was a period, very brief, of rapid expansion. That is called inflation. And theory, it's theory, but respectable theory. And the theory also predicts that this inflation generates gravitational waves. Now, what they would look like is basically ripples of gravitational waves, random ripples across the sky. A little bit like the cosmic microwave background that some of you may have heard of, except that's microwaves, this is gravitational waves. And in fact, this is a microwave picture I'm showing here. Okay, now, why is this important? It's important because it allows us to look back before the surface of last scattering. What is the surface of last scattering? When the universe was young, it was much smaller and much denser. And so light finds it quite difficult to propagate. It's a bit like a fog. If the fog is dense, you can't see very far. So when we look back to the earliest times in the universe, we can look back to about 100,000 years after the Big Bang, and then it's opaque, just like a fog. Okay? But the gravitational waves are neither scattered nor absorbed. So they don't care about the fog. And that allows us to see right back to the Big Bang in a way that we cannot see with electromagnetic radiation. The third kind of astronomy you can do is to look at cosmic explosions like supernovae or gamma ray bursts. Here again, Hubble Space Telescope picture of the Crab Nebula, which exploded in 1054 AD and was widely recorded by Chinese astronomers. And you can also look for periodic signals from things like rotating neutron stars. So something that is dear to my heart is if you have a rotating neutron star with a little bump, a little mountain on it, it's like a millimeter tall, that mountain, but still we call it a mountain. Then as that neutron star spins, it emits a periodic signal, which is there forever, like a pure tone, and you can look for that. Now, the sad thing about those pure tones is they are weaker, much weaker, than the other things we've been talking about so far. But the good thing about them is they're there all the time. It's not a burst. So anyway, we're looking, LIGO and indeed our group here looks for these things. And what you learn from this kind of astronomy, you learn about the behavior of very, very dense matter, matter which is in supernovae and in neutron stars, matter which is like 10 to the 15 times denser than water, and magnetic fields which can be 10 to the 15 times bigger, that's stronger than the magnetic field on the Earth. So again, things that you cannot possibly replicate here. Just as light has a spectrum of colors and radio waves and everything else, so too gravitational waves. And what you're seeing here in the top part of the diagram is the sources in the sky that can make different types of waves. And at the bottom you see the detectors, the machines that you need to build to detect different kinds of things. So if you're interested in waves that maybe have 100 cycles a second, you use LIGO. We've discussed that already. But if you're interested in waves which make a cycle every minute or a cycle every hour, then you need to build a LIGO in space. That's the so-called LISA. And this is very interesting. Giant galaxies merging together make these sorts of waves. If you're interested in waves that make one cycle every year, then you use something called a pulsar timing array. I'm not going to go into that here in the interest of time, but just to note that this is a very cool project, and actually Australia plays a leading role in these pulsar timing arrays worldwide, and we are also involved here at Melbourne Uni. And if you are interested in waves which make one cycle every age of the universe, then you go and look at the cosmic microwave background polarization, which again is something that my colleague Christian Reichardt here at Melbourne Uni is studying. Okay, and just for fun, here is the LISA Pathfinder. So this was launched successfully a couple of months ago. It's a little satellite. It's a technology demonstrator. So it has all the bits and pieces for the full LISA just on one satellite. And it's currently flying out there testing the technology and producing good data. When the full LISA is built, let's hope in 10 years' time, what you'll have is 3 of these satellites in a giant triangle, joined by lasers on two arms, and with mirrors in each satellite. So it's just like a LIGO, but in space. And the length of the arms is about 1 million kilometers. So a gigantic LIGO. And here, just for fun, is the launch, the European Space Agency launch control room. And there goes LISA Pathfinder, safe and sound, and currently returning excellent data. Okay, so let me finish now. A historic discovery. 100 years ago, Einstein predicted that mass and energy curve space and time. And then also predicted that if you have accelerated moving masses, moving energy, then you will get a ripple in the curvature of space and time, gravitational waves. 100 years later, in September last year, those waves were detected for the first time. And it's actually quite interesting to reflect about that. It's very rare in physics that you have to wait 100 years for a detection to be confirmed or refuted. When I'm preparing the talk, I was trying to think of examples. It's actually hard to think of an example. In mathematics, you sometimes have theorems that remain, or conjectures that remain unproven for many more than that. But that's a different situation. These are real physics experiments, real physical phenomena. Very, very rare to have to wait for 100 years. And that tells us two things. Firstly, it tells us that the initial prediction was unbelievably profound, and in many people's eyes, a long time ahead of its time. The second thing it tells us is that detecting them is hard, as we've seen. And a lot of things, I mean, it requires a lot of persistence, a lot of energy, a lot of long-term thinking, a lot of long-term investment, but it also requires many things to fall into place. You know, without inventing the laser, you can't build LIGO. We needed quantum mechanics to build LIGO. You need giant computers to analyze the data from LIGO. So all of these technologies need to be present before you can make a detection. So sometimes, you know, I guess as they say, for good things, sometimes you have to wait for good things, and this is an example of that. The LIGO scientific collaboration is fantastic collaboration, and they really live this ethos of long-term thinking and long-term planning and investment and good science and everything else. And we're at Melbourne Uni, we're very privileged to be a part of that collaboration and a part of this discovery. I will finish there. Here is a beautiful picture of a very pensive Einstein. And I thank you for your attendance and your attention. Thank you very much.
Are you happy to answer some questions?
As many as they like, no problem.
Well, thank you very much indeed, Andrew. That was a good report. Would anyone have any questions they would like to ask?
Yes, Professor, thank you for organizing that. I have two questions. How much universe Albert Einstein different by real universe? In other words, does nature reality is reality or illusion or delusion? One. Second question, how we reject gravity wave, how we improve it?
Okay.
Thank you.
So, no, they're good questions. So the first question, really I'm not qualified to answer. That's a philosophical question. But what I would say about that is, what a physicist thinks about reality and whether it's delusion or whatever, is that, well, maybe my opinion, it is very difficult to make predictions about anything. And we know that from common experience. You try to predict the stock market and you lose money. Everything is hard to predict. So if you have a framework like physics, which allows you to make predictions about certain things, they're very limited things, they're not everything, it doesn't tell you about love, but it tells you about some atoms, and it tells you to high accuracy, then that prediction, which is then tested by experiment, you should feel that you are learning. That can't happen by accident. That cannot be delusion. Now, is it reality or something else? I don't know, but it is not delusion. It's something important. What to call it, I don't know. The second question that you asked is how to improve on gravitational waves and how to reject them. Very good question, because, of course, any scientific theory can only ever be disproven, never proven. So you have to have a way of rejecting. And the way you would reject is that you, for example, look and you don't find, in this case. Unfortunately, in this case, it's not an experiment on the desktop in your lab, in the office, where you can go and, tweak the screws and do this and do that and just challenge the theory in many different ways. Here, unfortunately, we have to wait for the universe to send us a signal. But, and so again, I don't think anybody would say that this result, I think everybody would agree, proves the existence of gravitational waves. It's very hard to imagine any other thing that could be mimicking this. But it's not a proof that the whole theory is correct and we understand everything about gravitational waves. Absolutely not. We have to wait.
Well, thank you for that description of how LIGO works. What I noticed is it's different from what I've read in other journals.
Yes, I understand. It's a good question. So the question was, sometimes you hear it said that LIGO works by stretching, like the arms stretch and squeeze and the lasers can measure. Now, when they say that, it's just colloquial speech. They're not actually saying that the concrete tubes of the arms are stretching and squeezing, because then if that was what they were saying, then you're right, the elasticity of the material suddenly becomes a very important factor. That's not what they actually mean, it's just loose language. When they say the arms are stretching and squeezing, what they mean is the distance between the mirrors and the home base at the centre is stretching and squeezing. So in fact, the two things are exactly equivalent. Now you said also the mirrors are hanging off masses. Actually, the mirrors are the masses. So those mirrors are about 40 kilos, and they are suspended. You don't need any other masses there. There's the mirror, which is the mass. It plays a dual role, both a mirror and a mass, and it is suspended. And then as the gravitational wave passes through, the mirrors move, which is equivalent to the arms stretching and squeezing, as long as you don't think that means the tube. It's just the length of the arm.
Yes.
Do gravitational waves obey, do they work similar to light? Do they obey an inverse square type law? Do they get weaker the further they propagate?
Yes, very good question. Do they get weaker the further they propagate? Absolutely. And they do obey an inverse square law as far as we know. I mean, yet to be tested, right? But everything is consistent with that. But a very interesting thing about gravitational waves. So the inverse square law says that the amplitude, says that the sort of energy flux, as we would call it in physics, of the wave goes down as 1 over the distance squared. And the amplitude of the wave goes down as 1 on the distance, okay? So what that means, very important for LIGO, is if you can improve your sensitivity by a factor of 2, for example, that means that you can see things twice as far, and therefore you can see a volume which is 8 times bigger. So an increase in LIGO's sensitivity by a factor of 2, which we're really hoping we can do, is going to increase 8-fold the rate of the events that we see. And that's in the offing. That's going to come pretty soon.
Okay, up there, yes.
How do you correlate these black hole merging events with the gravitational wave you're detecting?
I see, yeah. So how do you correlate the black hole mergers with the gravitational waves you're detecting? If I understand the question, then Einstein's theory of relativity plays a big role here. So in Einstein's theory of relativity, you can compute very accurately what two black holes that are merging would produce as a gravitational wave signal, okay? And it doesn't depend on a zillion different things. It actually depends on, I don't know, I can't quite remember, but it's like 10 numbers describe it completely. Now you could say, maybe Einstein's theory is not right? Or maybe something else is happening in the way or whatever, although they're not scattered or absorbed, so that's not really likely. But still, in the pure theory, you predict a tone from the merger, and it just depends on these, let's call it 10 numbers. I don't quote me exactly, but it's something like that, okay? So now you go and look, and you take the tone that you heard, and you map it back to that theory and see, does it make sense? And that's what they've done. So it's not 100% confidence result. There could be something else that managed to look just like this. But believe me, it would be unusual. That would be really quite a coincidence because the setup is quite constrained.
Just behind you first, yeah.
I just wanted to ask you, before they built LIGO, did they have to detect black holes of that size before they engaged in the building of LIGO?
That's an interesting question. So they started the building of LIGO in, depending on how you count it, sort of mid-90s. We have detected black holes of this size, but indirectly. We've detected them through, it's sort of a long story, but we've detected them through, sometimes you get these black holes, they have disks of material around them called accretion disks. And those accretion disks emit X-rays. and optical light and this sort of thing. And you can do modeling of these X-rays and optical light. You could just see with normal telescopes. And you can infer, right, that there is a black hole inside, which might be, say, 20 times the mass of the sun. But, I mean, Rachel is actually an expert on this. I think, I mean, they're strong inferences. Almost everybody would believe them, but it's not quite the same as something like this. It's a more dirty system, in a way.
I'm just wondering, is focus a possibility so that you may, some future time, identify a location?
That's an outstanding question. So the question was, can you focus the detector and ultimately get a location? Unfortunately, with just one detector, the wavelength of the waves is like, you know, if it's 100 hertz or whatever, is like maybe 300 kilometers. And the detector is only 4 kilometers. So you have no localization at all. But once you have two detectors separated by more than 1,000 kilometers across the continental US, then you do get some localization. But remember, if you've just got two, all you know is that the source was somewhere on a circle in the sky. So you need a third one. Now, the Pisa detector, Virgo, is, you know, going up and running, was up and running, and will soon be up and running even better and stuff. Once you've got three, you can do some sort of localization, but it's not great, actually, but it's better than nothing. So you get it about sort of 1 square degree on the sky. The problem with that is, of course, then what you want to do, which is what your question is suggesting, is take every other telescope in the world and look in that spot to see whether there was something interesting. And unfortunately, 1 square degree of the sky is just packed full of stuff. There's so much to look at there, so it'd be very hard to narrow it down. But as you get more detectors, you get better localization. There was a plan to build a detector in Australia. Around 2010, 2011, one of the LIGO detectors was, there was a suggestion that it might be moved here. Having a detector in Australia, or actually just the southern hemisphere, is a huge improvement because all the northern hemisphere detectors are sort of roughly in a plane. And so to get really good triangulation, really you want one which is out of that plane. So I think, you know, one day that will happen and then we'll have better, yeah.
Perhaps just one more question. Okay, up to yes.
Why is there a time difference between the receiving of the waves, the two stations?
Oh, because the wave is like a wave front, right? Like, you know, like a front of weather. You know, it comes, it's like a sheet, and so the wave comes from some direction, who knows what. It's going to hit one of the stations first and then hit the other station. And it's traveling at the speed of light. You know, we can test that. And so it takes about a millisecond or 10 milliseconds, whatever it was, to go between them.
Okay, well, I just want to finish up by saying a very, very big thank you to Andrew. It's a very thoughtful and a very erudite lesson in gravity, and I hope you've all enjoyed it here tonight. So thank you very much.
Thank you.